morning. Today I am here to discuss the topic axiomatic approach to probability. In the previous section, Asim already explained the topic. So let's try to recap. So axiomatic approach is introduced by a Russian mathematician Kolmogorov in 1933. So in this approach, probability is not defined directly. Instead, a set of axioms or postulates is provided and probability calculations are based on them. This approach provides a logical and mathematical foundation for probability and incorporates ideas from both classical and empirical probability. So, before understanding the axiom, we must know some important terms, which is already explained in the first two sections. So first term is random experiment. Random experiment means an experiment whose outcome cannot be predicted with certainty. For example, tossing a coin, rolling a die, etc. Then next one is outcome. Outcome is the result of sample space. Sample space means the set of all possible outcomes of a random experiment. Example, tossing a coin. When we toss a coin, sample space is equal to head of A. Or when we roll a die, the sample space will be uncommon. This is the example of sample space. Then next term is event. Event means any subset of sample space. For example, consider an event of getting an even number. When we roll a die, consider an event of getting an even number. So the event of getting an even number is that is 2, 4, 6. This is an example of event. Now let's get into the topic axiomatic approach. So axiomatic approach is another way of describing probability of an event, and in this approach some axioms or rules are depicted to us. So these axioms are, there are 3 axioms. First axiom is axiom 1 or non-negativity. Or we can also say positiveness. It means that 0 greater than or equal to P. For any given event, the probability of that event must be greater than or equal to 0. This is the axiom 1. Next axiom is axiom 2, or we can say normalization or also certainty. It means that the probability of sample space is equal to 1. Then next axiom, axiom 3, also known as additivity. If two events A and B are mutually exclusive events, that means they cannot occur together. Such events, if two events are mutually exclusive event, then probability of A union B is equal to probability of A plus probability of B. This is the third axiom, or also known as additivity. These axioms are called a Kolmogorov axiom. Then when we consider sample point means sample point is a single possible outcome of a sample space. Then we can write these three axioms like this: 0 less than or greater than or equal to probability less than or equal to 1 for each if we consider a single possible outcome of a sample space. That is, if sample space is like omega 1, omega 2, etc., omega n. If we consider a single sample point, then we can write like this. Next one is probability of omega 1 plus probability of omega 2 plus is equal to 1. This is the second one, and third one you will write for any event A. Probability of A is summation of probability. If we are considering a single outcome, we can write these axioms like this. So now let's answer that. We can, by using these three axioms, we can prove some useful theorem. So theorem 1 is P of A plus P of A complement equal to 1. So we know that A complement means all outcomes in sample space that is not present in A, that is A complement. So we know that A union A complement is equal to sample space. So probability of A union A complement is equal to probability of sample space. From the axiom 3, we know that probability of this will be equal to probability of A plus probability of A complement. That is equal to so we know that P of X is equal to 1. So probability from axiom 2, we know that probability of sample space is equal to 1. So P of A plus P of A complement equal to 1. This is one theorem. Now moving to the next theorem. Theorem 2, we know that we want to prove that P of A is less than or equal to 1. So A means an event. An event is a subset of sample space. So a probability of event is subset of probability of sample space. This is equal to 1. So probability of sample space is equal to 1 from axiom 2. So probability of A less than or equal to 1. From the first axiom, we know that probability probability of A is greater than or equal to 0. So we can write that we can write like this. So probability will be always between 0 and 1. Then moving to the next theorem. Probability of 5 is equal to 0. This is theorem 3. So to get this, we will consider S complement is equal to 0. Sorry, 5. So S union S complement will be S from the axiom 3. Probability of S union S complement is equal to P of S. As S complement is 5, we can write like this. P of S plus P of X complement is equal to P of S. So here, taking by this, we will get P of S equal to P of 5 is equal to 0. By taking this into this side, we will get P of 5 is equal to 0. Then there is one more theorem we want to do, that is theorem 4. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So consider this as A, this as B. So I take this as 1, 2, 3. So from this, B of A is equal to P of 1 union 2. See? So we can write this as P of 1 plus P of 2. Then P of B is equal to P of 2 union 3. That is equal to P of 2 plus P of 3. So let's give to this equation. P of A is equal to P of 1 plus P of 2, that we can write as here we know A union B is equal to 1 union 2 union 3, and P of A union B equal to P of 1 plus P of 2 plus P of 3. Plus P of 3. So P of 1 plus P of 2 is equal to P of A, and P of 3 we want to find from here, that is equal to P of 3 equal to P of B minus P of 2. So here we will get P of P minus P of 2. So P of 2 is actually the intersection. So P of 2 we can write as A intersection B. So we will get P of A plus P of B minus P of A intersection. So the fourth theorems are proved. Next week we will move to a problem. So, let's say we have an urn means a container with 5 red balls and 3 black balls. We want to draw a ball from this bag. Find out the probability of taking a red ball. So here probability of picking a red ball. Here we have 5 red balls and 3 black balls. So we want to find here probability of picking a red ball. So number of favorable outcome here is 5 and total number of outcome is 8. So probability of getting a red ball is 5 by 8. So the question continues. For the above experiment, verify that probability of getting a red ball and probability of getting a black ball follows the axioms of probability. So let's define 2 events. That is, R is getting a red ball and B is getting a black ball. So from here we know that probability of getting a red ball is 5 by 8. Similar way, probability of getting a black ball will be 3 by 8. So we know that 5 by 8 and 3 by 8 lies between 0 and 1. Between 0 and 1. So the first axiom is satisfies first axiom. Then the second axiom is when we add the both, we will get 1. That is P of sample space is equal to 1. So P of R plus P of B equal to 1. That is 5 by 8 plus 3 by 8 is equal to 1. In the next, these are mutually exclusive events. Because these two doesn't occur together, that's why we can write P of A union B equal to P of R union B is equal to P of R plus P of B. That is P of R is equal to 5 by 8 plus 3 by 8 is equal to 1. So thus all the three axioms are satisfied. So the above experiment follows the axioms of probability. This is the problem. doubt, you can ask. That's it. Thank you.